All right, good evening, young people. This is Mr. Williams, and I had several requests from regular and AP Physics for me to make a video about um, how to answer this question. How far do you go altogether while accelerating? The answer to this question, what I'm going to do tonight, perhaps formally might be called a graphical derivation of the kinematic equation without final velocity. That's a lot of big words. You don't need to worry about it right now. You may not need to worry about it ever. I don't know. It depends on your future plans. But in any case, I'm going to repeat in this video what I have done in class several times already for most of my classes already this year, so that you can watch it at home and watch it slowly if you need to, and hopefully answer any questions that you might have. In preparation for this video, I have taken some graph paper and I made a velocity in meters per second on this, and every tick mark's 1. This is time. Acceleration in meters per second squared, and every tick mark here is 1, and here's 1. This is time. And then this bottom one is position versus time. Every tick mark is 2, so 2, 4, 6, 8, 10, up to 40. And tick marks are 1 here. All right, let's go ahead and get started. I'm going to show you a graph of some motion, just like I did in class. I'm just going to make some marks here. Let's say you're moving at 2 meters per second, and you do that for 1, 2, 3 seconds. And then you start accelerating at 2 meters per second. So every second you speed up by 2 more seconds. For every second that goes by, you speed up by 2 more meters per second. So you do that for 1, 2, 3 seconds, and then you move at a constant speed for a little while. Yeah, that seems reasonable. All right, let's see here. Drawing straight lines is always a challenge for me, so I'll use my ruler. Let's make the corresponding acceleration versus time graph. So the slope of the velocity versus time is 0 all through here. And then the slope here is rise over run. Rise is 2, run is 1. So it's going to be 2 all the way along to here. And then the slope is 0 for the rest of the way, which comes out to here. Now let's make our position versus time graph. I've already shown you how to do all this, so this is all review. Let's assume that you start at, position is equal to 0 at time is equal to 0. So you start here. In the first second, you go 2. So 1, and every tick mark is worth 2 here. In the next second, you go 1, 2. In the next second, you go 1, 2. There we go. So that's 2, 4, 6. 2, 4, 6. In the next second, you go 1, 2, and half of 2, which is 1. So 1, 2, 3, 3 more. 1, 2, 3. In the next second, by the way, before I get all too caught up, these 3 points are a straight line. All right, because c is a constant velocity, so it's a straight line for position. This next one up here, I'm going 1, 2, 3, 4, and half of 2, which is 5. So 1, 2, 3, 4, 5. And then here in this time frame, I go 1, 2, 3, 4, 5, 6, and half of 2, which is 7 altogether. So 7 up from here. 1, 2, 3, 4, 5, 6, 7. That puts me there. So I went 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 1, 2, 3. So I'm going up by 2 each time. Then here, the rest of the time, I'm going to go at a constant velocity. So I'm going to go the same distance each second. 1, 2, 3, 4, 5, 6, 7, 8. That's 8 each second. So I don't want to have to count them all. 8 times 1, 2, 3, 4. So 8 times 4 is 32. And I'm right now at 21 plus 32. I'm not sure I want to go that high. I'm confident I don't want to go that high. I'm just going to change my graph so I don't have to go that high. I'm going to erase this last data point. Ha! Ain't that nice? So 1, 2, 3. That way I only have to go up 24. Yeah, that'll work. I have enough room to go up 24. So then over 1, 2, 3, that's 8 and 16 and 24. And I'm at 21 plus 24 is going to be 45. So this is 40. I'm going to go across to here. 40 for 1, for 2. I just don't want to have it up in this graph, so I'm going to erase this one too. Sorry guys, I guess I should have thought about this a little bit more. I'm only going to go up I'm only going to go up 16. So let's just do it. 1, 2, 3, 4, 6, 7, 8. 1, 2, 3, 4, 5, 6, 8. Oops, on the wrong line. One, two, three, four, five, six. I'm a little tired because I made this video once and it didn't upload properly, so now I'm making it again. I am tired and I want to be at home. It's like, I don't know what time it is. It's 5 minutes to 7. Oh, Lord. Okay, 1, 2, 3. 1, 2, 3. So this is a straight line because we're going at a constant velocity. This is a straight line because we're going at a constant velocity. The steepness of this line is lower than the steepness of this line, and that makes sense because this velocity is lower than that velocity. Now here we're speeding up, which means no straight lines. We got curves. So it's going to be hard to draw a curve, like I told you in class. I had a friend of mine who was an artist. I am not a visual artist, so a friend of mine told me to use small brush strokes and then make them darker later. So that works out pretty well, even for somebody like me who can't draw. Just use tiny little brush strokes. I wish I had the time to take an art class, but I'm at a point in my life where I don't have that time. So anyhow, this is a curved line because you're accelerating. Now that we are done drawing the basic graphs, it's time for us to derive the kinematic equation. I'm going to start with a fairly simple argument. The area under this velocity versus time graph, right here, let's find that area together. So area is equal to height times base for a rectangle, multiplied by base. And the height here is 1, 2. So 2, 1, 2, 2 meters per second. So the height is 2 meters per second. And the base is 1, 2, 3, 3 seconds. So 2 meters per second times 3 seconds. So 2 times 3 is 6. And meters per second times second. This second is in the numerator. This second is in the denominator, so they cancel out. And you're going to get 6 meters. That should make sense, because down here, after 1, 2, 3, after 3 seconds, I went 1, 2, 3, 4, 5, 6. I went 6 meters. It matches exactly. The area under the velocity versus time graph is the distance that I traveled in that time. That's really nifty. So the symbol for this, A is 6 meters. Well, what is A? Is A position? Is A time? Is A velocity? Is A acceleration? Well, the area is your distance. It's the distance you travel. And in physics, the symbol we use for distance is x. So x is equal to, what was h? What was my height here? Well, height was velocity. So the symbol we use in physics for velocity is v. So the distance I travel is v multiplied by, and what was the base? The base here was time. See, time along the x-axis. So the distance we travel is velocity times time. That's an important equation. We're going to use it all year long. And this is how far you would go if you are not speeding up or slowing down. So if we were not accelerating, we would go this distance. But my question is, how far would you go altogether while accelerating? And the only time I'm accelerating is right here. Here's the next part of my argument. My initial velocity, if I just kept going my initial velocity, I would go some distance, right? I would, now I'm not going at my initial velocity, but if I were to go at my initial velocity, I would go this distance here. So how far would I go if I kept going at my initial velocity? Well, the area is equal to the height times the base, which is equal to 2 meters per second times 3 seconds. So that is, I cannot write well tonight, probably because I'm so tired. This is 2 meters per second times 3 seconds. So that means altogether 6 meters. I'm going to rewrite this equation. I'm going to write it a little differently than this. So the distance I would travel base, by base travel, I mean just how far I would go only if I kept my initial velocity, is equal to h. Now my h is my initial velocity. My initial velocity is 2. I have a final velocity, but my initial velocity, if I were to keep my initial velocity, so this is v subscript I. I didn't need an I up here because I was going the same velocity all the time. But here I need an I because my velocity changes. So my initial velocity multiplied by the time. So my base distance is equal to my initial velocity times my time. That's how far I would go if I didn't speed up. But I do. And when I speed up, I have all this area here under this triangle. How am I gonna figure that? Well, I could count it. But that kind of defeats the purpose because you probably don't want to be stuck drawing graphs for every motion all year long. It would be nice if we could come up with an equation, a general equation. And that's my goal here tonight. So this triangle here, I know the base is time, but what am I going to call this? I could call it something about velocity. Well, I have a trick for you, teenagers. Some other bright person came up with an idea I'm going to share with you. Let's skip down to our acceleration versus time graph and look at the area under the acceleration versus time graph curve. So this area here is equal to, of course, height times base, which is, the height is 1, 2, it's 2 meters per second squared, 2 meters per second squared, multiplied by the base, and the base is 1, 2, 3 seconds. And that's going to give us, 2 times 3 is 6. 6 watts. Now, people have trouble with this, so I'm going to do this one. This is meters in the top times seconds in the top, meters times seconds, over seconds squared in the bottom. Seconds squared is seconds times seconds. Look, if you have seconds in the top and bottom, they become 1. So they're gone for practical purposes. So this answer becomes 6 meters per second. 6 meters per second. Well, where's 6 meters per second in this picture up here? It's not here. This is 2 meters per second. And it's not 1, 2, 3, 4, 5, 6, 7, 8. It's not 8 meters per second. Where's this? Oh, the 6 is the difference. Look. 1, 2, 1, 2, 3, 4, 5, 6. Oh my goodness. Look at that. This side of the triangle is this. What is this? What is, in words, this is the change in the velocities. How much my velocity changed from my initial to my final. Oh, so this is change in velocity, and that's what A is. A is 6 meters per second. So this is the change in my velocity. And what is that equal to? Okay, what is that? This is acceleration, 2 meters per second squared. So it's equal to acceleration times time, the amount of time that it took. Oh, okay, so that's a nice equation. I like that equation. In fact, I'm just going to mark it off here. It's so good, we may want to consider remembering that since we did all this work to figure it out. So the change in my velocity is equal to acceleration times time, which means that the side of this, we could call it delta V. That's one possibility. But another possibility, I'm going to choose another way to call it. I'm going to name it acceleration times time. Okay? Because either one of these names would work. You can call it either one. And this here, of course, is time. What if I wanted to find the area here? What would this be? What would this represent? Okay, so this, kids, would represent the extra distance that I would go caused by me speeding up. See, the green is the distance I would travel if I went at a constant speed. But the extra distance I would go due to me speeding up or accelerating, actually, acceleration could be slowing down too, but we're not getting into that right now. The extra distance I would go due to speeding up would be this area here. Okay, so this is the rectangle. And I don't want to find all of this area. I only want to find part of it. I only want to find half of it. So the area here is going to be 1/2 of height times base, which is going to be 1/2 of AT times AT multiplied by, and my base is T. So that's 1/2 of, what was my A? My A was 2 meters per second squared, 2 meters per second squared, times my time was 1, 2, 3, 3 seconds squared. So let's do that out. 3 seconds squared is going to be 9 seconds squared. The second squared is going to cancel with that second squared, so we got 9 times 2 is 18 times 1/2, which is 9. So this is going to be 9. Okay, so the seconds get squared and cancel with this square. What's left is just meters. 9 meters. 9 meters. So that's a distance. That is that's the distance extra that I would have gone. So if I were to write this out in letters, I would say that A is my distance extra, and that's going to be equal to 1/2 A, and then the T's multiplied together to give me T squared. So my base distance is V initial times time, and my extra distance is 1/2 of AT squared. Let's see how far altogether. 6 plus 9. 6 plus 9 is 15. Well, how far did I go while I sped up? Let's double check and see if Mr. Williams is telling the truth. Did I actually speed up by 15 from here to here while the curve was happening? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh my goodness, look at that. It worked. My base distance of 6 plus my extra distance of 9, I went 15 while I was speeding up. Well, that gives us a clue to the formula that we're going to need to use, and I'm going to write it in ink down here. So the change in our distance while we're speeding up is going to be equal to the change in distance due to the base plus the change in distance due to the extra. So let's make it a little more formal, like you might see in a math book or a physics textbook. The change in distance is going to be equal to, so my base formula is, sorry, this one, I'm pointing to the wrong thing. My base formula is here, the initial times time, plus, and my extra formula is 1/2 AT squared. And that, young people, is how you derive by graphical means the kinematic equation that does not include the final velocity. Thank you for listening. I hope this was helpful to you, and have a wonderful evening.